Okay, let's get started. So the first topic is algebra and expressions. So there's quite a lot of the stuff that you've seen during GCSE time as well. So for example, law of indices, they tend to ask more about fractional powers and negative powers. Surds, you should be able to simplify and rationalize these. So I've got a question down here that we can do for both surds and rationalizing. So solve the equation x plus root 12 equals x root 3, giving the answer as a surd in its simplest form. So part I, what we need to do is we need to get all the x's on one side first. So I'm going to get this x over here and minus it to the other side. So you get root 12 equals x root 3 minus x, like so. And then we're going to factorize out the x so we can get x just by itself in one place. So root 12 equals x root 3 minus 1. And then to get x by itself, just divide by root 3 minus 1 on the other side. So x equals root 12 over root 3 minus 1. Now it says in the question to write your answer as a surd in its simplest form. So it doesn't necessarily say rationalize the denominator, but they're assuming that you will already know to rationalize the denominator. So to rationalize the denominator, I'm going to times both the top and bottom by root 3 plus 1. And you should be all aware of how to expand that. So I'm just going to write the answer to this. And that gives you 6 plus root 12 over 2. The root 12, you can put that as 2 surds. So that gives you 6 plus root 4 root 3. 4 times 3 is 12. And the reason why we've done root 4 is because that's going to give you 2. So we get 6 plus 2 root 3 over 2. The 2's will cancel out in the second fraction. 6 divided by 2 is 3. So our final answer is just 3 plus root 3. Okay, and then II says solve the equation 9 to the power of 3x minus 1 equals 3 root 3. We're going to have to use our indices rules here, and we need to get both sides to have the same number, so we can use our indices rules. So you know that 9 can be written as 3 to the 3 squared. So 3 squared to the power of 3x minus 1 equals 3, and then the root 3 can be written as 3 to the power of half. Using our indices rules, we know on the left-hand side we can do 2 times 3x is 6x, 2 times 1 is just minus 2. That equals, over here we've got a 1, and then when we're timesing 2, which have the same base, we just add the powers. So we've got 1 plus a half. So we've got 3 to the power of 3 over 2. Now all we need to do is just make both sides equal to each other. So the 6x minus 2 equals 3 over 2 in order to find, because you've got the same bases on each side. So 6x minus 2 equals 3 over 2. 6x equals 3 over 2 plus 2, so 7 over 2. Then x just equals 7 over 2 divided by 6, which just gives you 7 over 12. That's your final answer. So they can ask you your GCSE surds and indices rules for this as well. Okay, moving on. So we've got completing the square here. So express x squared plus 9x plus 3 in the form x plus a squared plus b. Now remember, the relevance of actually completing the square of quadratics is to find the turning point of that quadratic. So it could be a minimum point, or it could be a maximum point as well. You can also use differentiation for that as well, but you can also use completing the square as well. If they force you to put it in this form, you have to use this form. You can't just use your differentiation method. So all we're doing is we're doing x plus half the middle number, so that's 9 over 2 squared. And then we do 9 over 2 squared, and we're minusing that, which is minus 81 over 4. And then we're just plussing the 3 that's there. Simplifying that, we get x plus 9 over 2 squared. Minus 81 over 4 plus 3 gives you minus 69 over 4. Part B says state the coordinates of the minimum point of the curve. All you do is you take the opposite sign for the inside, and then you just for the x, and then take the outside for the y. So we've got minus 9 over 2 minus 69 over 4. So that's the turning point where the gradient is essentially 0. Let's have a look. So we're done completing the square. Now algebraic fractions, this tends to link quite well with integration as well. So what you do is the first part of the exam question tends to say, okay, put this fraction in an algebraic fraction, express it as its terms, and then the following question will say therefore or hence solve this by integration using what you've just done. So algebraic fractions is two different examples I've done. So this one here, quite straightforward. Express x plus 5 over x plus 2, x plus 3 in this form here. What we're essentially doing is equating coefficients. So we've got the top equation, x plus 5 equals, now you're combining these bottom two expressions together. So you want the first one to be over x plus 2, x plus 3, and the second one to be over x plus 2, x plus 3. So to do that, for this first one to be over x plus 3, we need to times the top a by x plus 3 as well. And with that b, for that to be over x plus 3, x plus 2, I need to times the top by x plus 2. Let's expand that. You don't have to expand, actually, you can leave it like that. So now we need to eliminate either the a or the b so we can solve what x is. So let's let let's let x equal minus 3. And the reason why we're doing that is because we want this to equal 0, and then we can find out what b is. So minus 3 plus 5 is 2 equals, this term here will give us 0. And then we've got x plus 2, so minus 3 plus 2, so 1b. So we know minus 3 plus 2, sorry, minus b. So therefore, b just equals minus 2. So we found b. Now we can find out what a is. We can let x this time equal something to make this 0, so it'd be minus 2. So minus 2 plus 5 is 3, equals minus 2 plus 3 is a, and then that becomes 0, so a just equals 3. So just putting that into here, our final answer is going to be a, which is 3 over x plus 2, minus b, which is 2 over x plus 3. So that's the final answer with that one. Now, sometimes they can ask you, so if you look at the difference with the second one, they can have a little squared there as well. And they don't always give you the form to put it in. Sometimes they expect you to know that this is going to be 3 fractions. So make sure you memorize this as well. So this one over here is over x minus 1, x minus 3 squared. A really common mistake that students do is they'll say, okay, I'm going to express it as 2 fractions, a over x minus 1 plus b over x minus 3 squared. And then they forget this middle term here. So make sure you remember that middle term. They don't always tell you in the exam what form to give it in. So let's do exactly the same thing as what we did before. So we want the 5x minus 13 to equal, I want all these 3 terms over x minus 1, x minus 3 all squared. So times each of these letters by what would give you that. So a times it's already over x minus 1, so I just need x minus 3 squared. The b is already over x minus 3, so I just need 1x minus 1. And I need an x minus 3 to put on top. And then the c is already over x minus 3 squared, so I just need to times by x minus 1. And just like last time, we just need to let the x's equal a certain thing to cancel some out. So for example, I could let x equal, we can do 1 first, so we can eliminate this c. So let's let x equal 1. So I'm just going to put the working out in here just to save time. So minus a equals 4a. So essentially, letting x equals 1 makes this 0, and it makes that 0, so it gets rid of the b and c. We're left with just the a. So to get a by itself, divide by 4, minus 8 divided by 4 is minus 2. So we found our a. Now let's let x equal 3. And that will make this 0, and it'll make that 0, so we're left with just the c to find the c. So 5 times 3, 15, minus 13 is 12. Equals, that becomes 0, this also becomes 0, and then 3 minus 1, which we've got 2c over here, so therefore c just equals 6. Hold on, did something wrong here. That should be 2, don't know why I wrote 12 there. 15 minus 13 is 2, so c just equals 1. Now we need to find the b term. Now, if we plug in x equals 1 or x equals 3, that's going to eliminate it and make it 0. So we need a number that's not going to make it 0. So let's just let x equal 0, because we already know what a and c is anyway, so we can use that to help us as well. So let's let x equal 0. So, and then we've got minus 13 equals 0 minus 3 squared. But we know what a is as well, so I'm just going to plug this in. So 9a plus 3b minus c. Plug in our a and c that we know. So we get minus 13 equals minus 18 plus 3b minus 1. And then solving that, we just end up getting b equals 2. Then finally, you just need to put it into your fraction. So you get a, which is minus 2 over x minus 1, plus b, 2 over x minus 3, plus c, plus 1 over x minus 3 squared. So yeah, common mistake, people forget that middle fraction. So just make sure you don't forget that middle fraction. Okay, next we've got proof. So proof by contradiction, this is quite a common one that tends to come up in the exam. Proof by contradiction is essentially when you're contradicting yourself, so you see saying the opposite, and you're proving that the opposite isn't true. So therefore you contradict yourself and then you prove essentially what's here. So use proof by contradiction to show that there exists no integers x and y for which 6x plus 9y equals 1. So you're going to contradict that and write your contradiction down. So I'm going to assume that there are integers x and y. So we're going opposite. We're saying there are integers rather than them saying that it doesn't exist. So assume that there are integers x and y for which the equation 6x plus 9y equals 1. And we're going to try and show that this isn't true, so therefore prove the original statement's right. So 6x plus 9y equals 1. Let me just write this down here. 6x plus 9y equals 1. If I factorize the left-hand side, we can pull out a 3. So 3 times 2x plus 3y equals 1. And then I can get the 3 over to the side. So I've got 2x plus 3y equals a third. Can't really do anything else with that. However, if you look at this, if we've just said that there are integers, x and y for which this equals 1, then if x and y are integers, so let's write this down. If x and y are integers, so whole numbers, then 2x plus 3y should be an integer as well. So 2x plus 3y should be an integer, which is not, it's equal to a fraction. So just to, whenever you get confused with these as well, just plug in some numbers and see what happens. So if I let x and y just equal 2, for example, 2 times 2 is 4, plus 3 times 2, which is 6, so 10. So we get an integer whenever we stick integers in there. However, this is equaling a fraction. So therefore, it's a contradiction. So contradiction. Because you'd say that there is no integers. You can basically say that it's equal to a third, which it shouldn't be. So yeah, something along them lines. You've just contradicted it. Okay, now this one's also quite common as well, so proving irrational numbers. I've seen this in quite a lot of past papers as well. So prove by contradiction. So again, you're going to basically say that root 3 is rational, but so prove by contradiction that root 3 is irrational. Now remember, irrational numbers are just numbers that continue forever. Rational numbers you can essentially write in a fraction. So we're going to say that root 3 is, we're going to assume that root 3 is rational. Now, if we're saying something is rational, it essentially means it's not continuing forever. So we can write it as a fraction. So I can say root 3, I can write it as a over b, where a and b are integers. So you need to give a and b are integers. Okay, so using this fact, so root 3 equals a over b. Let's get rid of the square root that's on the left-hand side. So we get 3 equals a squared over b squared, because you would get it as this, right? And then the squared applies to both the top and bottom. Okay. So if I can then times up the b, so from the fraction, so 3b squared equals a squared. So we basically need to prove that both of them are going to be multiples of each other. So I'm going to start off with the b first, because the a first, sorry, because I've brought b up. So looking at this, we can say that a squared is a multiple of 3. So think about your proofs again from GCSE, and they can bring them up here as well. So if you've got a number times by a letter which we've said is an integer, then it's going to be a multiple of that. So because we've said b is an integer, 3 times an integer, it's going to be in the 3 times table, so it's a multiple of 3. So if a squared is a multiple of 3, then a must also be a multiple of 3. I'm going to do the same thing again, but we're going to do it the other way around. So I'm going to introduce a different letter so I can get rid of that a, and I'm going to let a equal 3n. So just this on top equal 3n. So therefore, so this last equation that we've got here is 3b squared equals 3n squared. And we can let a equal 3n because we've just said that a is a multiple of 3. That's the reason we've let a equal 3n. So plugging that in, we get 3b squared. Let me do it over here actually. 3b squared equals 3 squared, which is 9, and then n squared. We can then this time get b by itself because we want to show that b is going to be a multiple of 3 as well. So getting b by itself, I'm going to divide by 3 on the other side. So I end up getting b squared equals 9n squared divided by 3 is 3n squared. So it's 3 times a multiple. So we'll do the same thing that we just did last time. So I'll do that a bit better. So b squared, multiple of 3. Because it's 3 times n squared. So if b squared is a multiple of 3, then b is also a multiple of 3. So a and b both have common factors. Let's write this down. A and b have common factor of 3. However, right in the start, we've said a and b are integers, and it's essentially in its simplest form. So that's one thing I forgot to write here, that it's in its simplest form, meaning no common factors. However, I've just proved, well, not proved, I've just shown that both a and b are factors of 3 when it should be fully simplified already. So we've just contradicted ourselves. So that's a contradiction. So with all rational number, irrational number questions, so with all irrational number questions where you're proven by contradiction, it's always the same method. So you're going to show it as a fraction, and then you're going to show that they're a multiple of each other, and you've essentially just contradicted yourself. Quite a lot of people just memorize this proof, but it's not too bad. But it does always tend to follow the same thing. Even if you're proving by contradiction root 2 is irrational, that's the same thing as well. Okay, so with binomial, this is what you're going to be given in the exam booklet, the formula booklet, sorry. And the reason why there's 2 versions in the formula booklet is because this, as you can see from here, n belongs to natural numbers. So this is the scenario when it's positive, and then this one here is when you've got fractional powers or negative powers. So that's why there's 2 different versions. So I've got 2 different questions that we can go through for this one. So let's have a look at this one here. So this one's a simple one. This is where the power is just positive. So find the first 3 terms in ascending powers of x of the binomial expansion 2 minus x over 8 to the power of 7. So let's do part A. So if we're using this one here, this top one over here. I'll try and keep that on screen at the same time. So we've got a to the power of n. So in this case, a is 2. So we've got 2 to the power of n, which is 7, which you can see there in the first part of the equation. And then we've got plus, we've got the NCR button. So we've got n, which is 7, 1. And then a, which we've just said is 2. And we're doing n minus 1. So 7 minus 1, which is 6. And then we've got b. B is just minus x over 8. Don't forget that minus sign that's there. So minus x over 8. And what I tend to do is, so these 2 numbers here should always add up to give you your total powers. So you'll see the pattern anyway. So we've got the first term, 2 to the power 7. Then we've got the second term, which will work out that way. The third term is going to be, let's have the right pen, 7, 2. And then we've got 2 to the power, we're going to decrease power by 1 again. So we get 5, and then we've got minus x over 8. This time, we're increasing the power by 1, so it's going from 1 to 2. So there's the first 3 terms. Just putting that in the calculator and simplifying it, you get 128 for the first term. You then get minus 56x plus 21 over 2 x squared. So just to reiterate, when you've got a positive power, you use this first equation in the formula booklet. That's why it says n belongs to natural numbers, which are the positive numbers. Okay, so f of x equals this here. So ax plus b times the expansion that we've just done, where a and b are constants. Given that the first two terms in ascending powers of x in the series expansion are these two, find the values of a and b. So what we can do is we're going to expand this out essentially, and because they've already told us the first two terms, so the number term and the x term, I don't care about this x squared term. I care about the x term and I care about the number term, so I'm not going to fully expand. So if I start expanding this, ax times 2, I get 2ax. Hold on. I'm not using this actually, I'm using what we've just worked out this here. So ax plus b times this here. So let me just write that down. Ax plus b times 128 minus 56x plus 21 over 2x squared. Obviously, this continues forever, right? But we've just stopped at 3 terms. So we're timesing this out. So ax times 128, that gives us 128 ax. 128 times b, so 128b. These two terms are fine because that's an x term and this is a number term. The one terms they've given us, so 384 is a number term and minus 104x is an x term. Okay, let's have a look at the next one. Minus 56x times ax, that's going to end up giving us x squared, so I don't care about that term. Minus 56x times b, however, is minus 56bx, so that's fine. And then all the other terms will not give us x terms or number terms, so that's it, we're done. This is what we've got. Now, essentially, this is equal to 384 and minus 104x. So the x terms, which is 128 ax, and we've got minus 56 bx, that's going to equal the x term, which is minus 104x. And the one that's remaining, so the 128b, which is the number, that equals to 384. So let's work out b first. That's quite simple. B just equals 384 divided by 128, which just is 3. So we found b. That's what we've done. Now we just need to find a. Now over here, the x's are all gone. So just to solve that, we know what our b is. So substitute the b here. 3. So you plug in 3 into that, and then solving it, I'll just write the answer. We get a equals a half. Just solving that. And that's how you find that. Okay, let's move on. Okay, so this time we don't have a positive power, we've got a negative power. The reason why we've got a negative power is because this 1 over 1 plus x squared becomes 1 plus x to the power of minus 2. So this time on the formula booklet, you're going to be using this bottom version of the equation because x, well, n belongs to real numbers, and that's the series part. So we're going to use that bottom one. Usually you might have seen this like as factorial, so that would be 2 factorial, for example, so 1 times 2, the next one's going to be 1 times 2 times 3, and so on. But in the formula booklet, they show it like that. So let's do this question using that one. So we've got 1 plus x to the power of minus 2, and you just plug in everything in. So if you have a look at the equation, we've got 1 as the first term. It's in the form 1 plus x, so that's the reason why we can use this bottom one here. So the first term is 1, and then we've got nx, so 1, n is minus 2, so plus minus 2x, and the next part says n times n minus 1 over 1 times 2x squared, so n, which is minus 2, and then we need to do minus 2 minus 1, so we get minus 3, and that's going to be over, if you have a look here, 1 times 2, which you know is 2, but I'll just write 1 times 2 so you can see the pattern. And then we're timesing that by x squared because it says it over here, x squared. Now the next one is going to be, let me just bring this down here. Okay, so the next term now we're going to do minus 2 times minus 3 times minus 4. Minus 2 times minus 3 times minus 4 over, not 1 times 2, 1 times 2 times 3. You can just see the pattern, times x squared, bring that up 1, so x cubed. First 4 terms, 1, 2, 3, 4. Yeah, that's the first 4 terms. If you were going to do the next one, it would be -2 times -3 times -4 times -5 over 4 factorial, 1 times 2 times 3 times 4, and then x to the power of 4. Okay, so just simplifying that, we get 1 minus 2x plus 3x squared minus 4x cubed. Okay, and then the terms for this being true is that the mod of x, so if you turn x positive, it has to be less than 1. So because we've used that, I'm just going to put the condition down as well. That's what we've used for the binomial expansion, and that has to be true. Okay, so let's have a look at the content checklist just for this first section. There's anything. So solving equations, you should be comfortable with linears all the way to cubics or quadratics and stuff as well. We're going to have a look at dividing out a polynomial right now in order to do that. Inequalities, modulus equation graph, so we'll have a look at modulus as well. So modulus is where we're essentially turning everything positive, represented by this sign. You should recognize in terms of the graph, we're bringing everything above the x-axis. Binomial expansion, factor and remainder theorem. So if something's a factor, when you plug in that factor, you should get 0. If it's not, then it's a remainder theorem. You get the remainder out of that. So let's have a look at that polynomial question. Okay, so use the factor theorem and division to factorize f of x completely. Now here, they've not told you any factors. So it's a matter of trial and error to find the factors. And it's using numbers that are essentially going to 10. So 10's even, we could try 2. F of 2, done this one earlier, so I can just tell you the answer. When you plug in f of 2, if it's a factor, it should equal 0. If it's not 0, then it's not a factor. You end up getting 36, so this is not a factor. So then you try another one. I tried the minus version of it, and then I ended up getting 0. So therefore, this is telling me that x plus 2 is a factor. Remember, you take the opposite sign whenever you keep it as an expression. Now, what you're doing is you need to divide this polynomial. So we've got 2x cubed minus 7x squared minus 17x plus 10. And we're dividing that by x plus 2. Now, I'm aware some of you do different methods than this, so you can stick with your method if you want to. But when you're doing this as well, make sure you leave gaps for each term. So what I mean by that is, for example, if I didn't have an x squared term, I still have to leave a gap here. So I would write 0x squared just so it follows through. Okay, so how do we do this method? What you're doing is, so x times something gives me 2x cubed because I'm cancelling out each term as I'm going down. I'm minusing as I'm going down. So what do I times x to get 2x cubed? Well, that's just 2x squared. And then you do 2x squared times 2, which is 4x squared. You then minus these from each other. So 2x cubed minus 2x cubed, that's gone. That's 0, as expected. They cancel out. Minus 7x squared minus 4x, we get minus 11x squared. And then what you do is you just pull the next term down, minus 17x. Now, write the same term here again. Now, what do I times x by to get minus 11x squared? That's just minus 11x. Then do minus 11x times 2, which is minus 22x. Minusing these from each other, they cancel out. And then for this, we get 5x. And then I'm going to pull that 10 down. So plus 10. So we've got 5x squared here again. Something times x gives me 5x squared. So that's just 5x. So put 5 on there, sorry. That's not even an x squared. That should be an x. Hold on. Don't know why I put squared there. Minus 17x minus 22x is 5x. Bring the 10 down. Something times x gives me 5x. That's just plus 5, so that goes there. So see how I noticed my mistake there as well. Had I wrote 5x here, that doesn't make sense. It doesn't follow the terms there as well. So keeping it all in order makes you spot your mistakes quite nicely as well. Okay, what do I times by x to get 5? We already put 5 there. So 5 times 2 is 10. As expected, you should get 0 there. If you end up getting a number there, this isn't a factor. You've gone wrong as well with that being a factor. So therefore, let me just move this to that side here. So therefore, we can write this f of x as x plus 2 times what's on top, 2x squared minus 11x plus 5. Now, we've not factorized it completely because we can factorize this quadratic out as well. So it's up to you what method you want to use to factorize that quadratic. You can use the AC method. You can use quadratic formula if you want it to be quick. So x plus 2 times it's 2x minus 1 and x minus 5 to factorize out that one there. And that's your final answer on how to factorize that completely. Okay, so the reason why I got this question is because I just wanted to demonstrate what set notation is. This is quite common for them to ask as well in the exam, present your answer in this form. So using algebra, solve this inequality. Now remember, whenever you're solving quadratic inequalities, it have to equal, well, it has to be more than or less than 0. I'm going to minus 15 to this side, so x squared minus 2x minus 15 is more than 0. So factorizing that, to find out where it crosses on the x-axis, we get x minus 5 and x plus 3. So I know it's going to cross x equals 5 and x equals minus 3. I can sketch the graph. So minus 3 plus 5, let's say it's over here, that's minus 3. That's plus 5. Where is this graph more than 0? Well, that's above the x-axis. So that's over here and over here. So for all values of x more than 5 and for all x values less than minus 3. So how do I write that in set notation? So in set notation, the way we write that is we say we're talking about x, and we've just said that x is less than minus 3. So that's how you write that in set notation. For x, I've said x is less than minus 3. Close the set for that one. Or, so the or symbol is represented by the u. X could be more than 5. So I'd say let x be x is more than 5 and close your set there. That's how you write in set notation. So we're given to two conditions what x could be, and because it could be either or, we've put that or symbol there as well, which is like that. If it was both conditions have to be true, you could just put the n. Just to note as well, when you've got the solutions down there, you wouldn't have that or symbol because it's just all values between minus 3 and 5. So I'll just show you an example of how to write. It would be x belongs to, if I was talking about these values over here, in set notation, the way you write that down is x is between, so x is between 5 and minus 3. So that's just represented in one single set because there's no or condition there. Okay, so yeah, that's how you write set notation. Right, let's move on. Wary of time as well. So the next section is functions and graphs. So you need to be aware of function notation, composite functions, which is functions in functions. So for this is functions in functions. So for example, if I had f g of x, you always work from the inner and then go outwards. So that's the inner, and then you always work out outwards. Your inverse functions are always the functions in which is reflected in the line y equals x. Domain and range. Domain is the x values that you put in. Range is the f of x or y values that they will be true for. Now remember, with inverse functions, they swap, which we'll have a look at as well. You need to know your transformations. You need to be quite confident with sketching standard graphs and also interpreting graphs as well. It's quite common for them to say sketch as well, so not necessarily an accurate like graph sketch, but just sketching. Okay, let's have a look at some of these questions. Okay, so the first question, the functions f of x are defined by these. Evaluate f g of 1. So what we're doing is first we're finding g of 1. So let me try part A. So we're finding g of 1 first. So you substitute 1 into there. So 2 over 1 plus 3. So just a half. You then plug in the answer into f. So we then do f of the answer that you've just found. So a half. And you plug in a half into there. So 3 times a half plus 4. So we just end up getting 11 over 2. So yeah, with composite functions, always do the inner one first and then the outer. Part B, solve this composite function equaling to 6. So that g f of x is g of what is f of x? F of x is 3x plus 4. So wherever x is in g, you're putting 3x plus 4. So 2 over 3x plus 4 plus 3. Simplifying that, 2 over 3x plus 7. And what we're doing is we're just making that equal to 6 and we're just solving it. So just basic solving. So 2 over 3x plus 7. Make that equal to 6 and solve it. I'm just going to put the answer down here just because of time. You should end up getting minus 20 over 9 for that question. Okay, swiftly moving on. So we've got a range function here. So we've got functions defined by this. Always try and visualize what do these graphs look like. So I've got a quadratic here. It's a U-shaped quadratic. X belongs to real numbers, so the domain, but x also has to be more than or equal to minus 1. Okay, so that basically means that this graph is sketched only for a certain amount. So the whole U-shaped isn't drawn potentially with this one. So let's have a look. Set the range of f. So what we're going to do first is try and factorize that. So f of x equals, so two numbers at times give you 1, add 2, just 1 times 1. So we end up getting x plus 1, x plus 1. So it's just x plus 1 squared. So therefore x is touching minus 1 when it's at the axes, as you can see from this definition here. So the range of f is, it has to be more than 0. The reason why is because this graph looks like this. So it's touching minus 1 like that, right? So that's minus 1. And we don't want all the values before that. So the domain is keeping it just to that. So we've only got just that part of the curve. So what is the range? Well, this can continue forever upwards that way. So all we're just going to say is that the range is going to be f of x is more than or equal to 0 because it's never underneath the axes, but it can equal to 0 because it's equal to 0 at that minus 1 point. Okay, part B, sketch the graph f of x and f of minus 1 on the same graph. Well, I've just done f of x over here, so let me pull this down over here. And it says draw f of minus 1 on the same diagram. They want you to understand that the inverse function is a reflection in the y equals x line. So if I draw the y equals x line just for your reference, there's the y equals x line. Let's actually label as well where it crosses on the y-axis, since it's there. We, when we let x equals 0, 0 squared plus 0 plus 1 is just 1, so that's 1. Now that's going to help when we reflect it down. So reflecting this in the line, we end up getting, since they're both 1 anyway, something that looks somewhat like that. So this is y equals f of x. This is y equals the inverse of f. So that's going to be minus 1. So whatever was up over here has gone down there. And then this, the one that was on the y-axis has come down to the x-axis. So that's the inverse of each other. Okay, and then part C, find an expression for f of minus 1 of x and state its domain. So what you do is, well, the method I use is y equals x squared plus 2x plus 1. And what you need to do is you just need to make x a subject, essentially. So you'd use the factorized version, make x a subject, and then that's your f to the minus 1 of x. I'm just going to put the answer down again just because of time. So f to the minus 1 of x equals root x minus 1. But that's the method you use. It says state its domain. Now, remember, since this is the inverse, the domain is the range of the normal f of x. And we know that the range was f of x is more than or equal to 0. So if we take that range that we found and make that the domain, x is more than or equal to 0. That's what they wanted to test you on. So they just flip over. Okay, let's do question 3. We've got a modulus one here. So sketch the graph with the equation y equals 2x minus 3. So what you do to draw this is first sketch the normal graph y equals 2x minus 3. What does it look like? It has a positive gradient, so it's going up like that, and it's crossing the y-axis at minus 3. So the graph somewhat looks like that initially. So that's where that's minus 3. That's minus 3. This over here, to work out where it crosses the x-axis, I just need to let y equal 0 and solve, and you end up getting 3 over 2. So to change this to the modulus, what I need to do is whatever's in the negative underneath the x-axis, I just need to reflect upwards. So all this negative part that's over here needs to come up. So therefore, it just becomes like that, where this is mirrored of the minus 3, so it becomes plus 3. So now I can just sketch the graph neatly. Let's just do part A over here. So part A, the modulus graph over here, we have like so, where it says state the coordinates, so that's 3 over 2, and this over here is just 3. Okay, have we done that? Yeah, part B. Find the values of x for which satisfy this being less than 9. So I'm going to just copy this diagram that we've just done. Okay, just so you can see. Okay, so I've got my graph there of the modulus of 2x minus 3, proving that that's less than 9. Essentially, y equals 9 is what we need to draw, which we can say is roughly, it's a sketch anyway, right? But it's going to cross two places like so. So this equation here, that's the going to cross at 9. So that's the y equals 9 line. And as we can see, it crosses two places. So it crosses over here, and let me do that in red so you can see that. It crosses over here, and it crosses over here. So we need to solve two separate equations in order to find that. For this, I'll call that number, oh, it's fine, it's okay. For this one over here, it's the positive version of the line. So it's 2x minus 3 equals 9. And then for this part over here, it's the minus version of the equation. So we've got minus 2x minus 3. So you just put a minus in front of that because remember, this blue part wasn't part of the original equation that we drew, the y equals 2x minus 3. It's the minus version of that equation. And then we're solving that. So we're solving two different case scenarios. So there's the first one, that's the second one. So for this one, you get x equals 6. And for this one here, I'm sure you're capable of solving that, is x equals 3. So there are your two functions. Part C says find the values of x which satisfy this being less than or, oh, hold on. I didn't realize it's an inequality. So I didn't finish that last question. Find values of x which satisfy the modulus equation being less than 9. So we found these two red points. Now, where is that modulus graph less than minus 9? Well, it's between them values. It's these ones here, right? So using them, I'll do my answer in red. X is between my numbers 6 and minus 3 because that's where it's between, right? So between 6 and minus 3. So it's a bit like the quadratic inequalities that we did as well. Okay, part C, same thing, solving the inequality. So first I need to sketch the graph. So I'm going to copy the graph again. Even if they don't tell you to sketch the graph in the exam question, so here they've told us, actually, which has made it quite useful. But if they don't, still sketch them so you could see what part of the modulus you're actually solving. Now remember, the gradient with this modulus graph is 2. Whereas the gradient with x plus 1, it has a gradient of just 1. So it's going to, we need to figure out where it's going to cross. So if this is a gradient of 2, a gradient of 1 is going to be more shallow, right? And it's crossing at the 1 on the y-axis. So it'll be crossing over here, and it's going to look somewhat, probably less steep than that. Somewhat like that. So that's my x equals 1 line. So I can see again, it's crossing two places on that graph. So we need to find them two red spots. So just like we did last time, I'll put a line here. I've got the minus version of the equation. So minus 2x minus 3 equals x plus 1. My second version is the 2x plus 3. For this second spot here, and that's going to equal x plus 1. So solving each of them scenarios, for this one over here, you get x equals 4. And for this one over here, we get x equals 2/3. Always check, does the answer make sense? Well, 2/3 makes sense being there, and 4 makes sense being there as well. Now, we want to solve where is this graph, the modulus graph, less than x plus 1. We can see that this is this section here. So we just need to sandwich them into one inequality. So our final answer is x is between 4 and 2/3. That's your answer. So again, it's similar to the quadratic inequality one. Okay, let's move on. I'm just a bit wary of time, so I'm just going to quicken up the pace a little bit. So we've got another composite function. So what you do is you substitute f of 4 into here, your answer, you then substitute into f. So I'm just going to write the answer down. You get 41/9 for that one. I'm going to send all these out anyway, so you can work on these independently as well. Part B, state the range of f. So what you need to do is you need to plug in numbers and see what happens. So if I let x equal 4, so when x equals 4, you end up getting 13/2 to 7.5 approximately. So that's the lowest that it can be because I can't put x equals 3 in, essentially. So what I'm going to do is I'm going to make the numbers bigger of x because x is more than or equal to 4. So let's let x equal 1000, for example. So if I let x equal 1000, I get 3 times 1000, 3000, 3001 divided by 1000 minus 2, so 998. If I put that in the calculator, it will show me what is tending to. So 3001 divided by 998, we end up getting 3.007, continues forever. If you even substitute a number like 10,000 in, you'll end up getting 3.000 something. So this is tending towards 3. So I've essentially got 6.5 for this, and we've got 3. That's what is between. So you need to sandwich that into a range. So we're going to say f of x it has to be less than or equal to 13/2 because that's the upper value, but it's getting closer to 3, so it's never going to be more than that. So that's how you sandwich it. Remember, the smaller one goes first. So yeah, you're just plugging in numbers and seeing what's happening, essentially. Okay, it makes sense as well if you think about it. That can't be 2 because 2 minus 2 is 0. You can't divide by 0, so it does make sense. Part C, state f of minus 1 of x and state its domain. So f of minus 1 of x, let y equal this, and then make x a subject, switch over the letter, and then that's your inverse. I'm just going to put the answer for that, and then you can work on that independently. So f to the minus 1 of x equals 1 plus 2x over x minus 3. It says state the domain. Now, because it's the inverse, it's going to be the range of the original function, which we've just found. So this range has become the domain. So it's x is less than or equal to 13/2, but more than 3. Okay, solve the equation. We've got 2 modulus graphs equal to each other. So what you have to do is you have to sketch each modulus graph, noticing that this has a gradient of 1 and this has a gradient of 2. So a lot of students as well just assume you're going to make the negative equal to the positive and then the positive part equal to the negative and vice versa. It doesn't always work like that, and you'll see that with this sketch. So let's sketch the graph. So the x plus 4 one, so y equals x plus 4 is going to cross that 4 over here. And then whatever's down here, I bring up there, right? So where this part is minus 4. So you sketch your graph for that. So that's x plus y equals x plus 4, modulus of x plus 4. Now let's do the next one. So we've got the modulus 2x plus 3. Now that's a gradient of 2, so it's going to be steeper than this line, right? So it's not going to follow this line, it's going to be a lot steeper. And it's crossing at 3, so underneath it's crossing, so it's looking somewhat steeper like so, like this. Hold on, and it's crossing over here. The point that it crosses over here is when you're solving it is minus 3/2, and then it's going to go upwards like so as well, so steep. So as you can see, this graph is never touching the negative part of the modulus of x plus 4. This is why it's really important to draw a sketch. Now, what you're going to do is, like the last questions, find them 2 red points. So I'm solving the positive part of the x plus 4 for my first scenario equals, I'm going to show you this for this one here, equals the positive part of 2x plus 3. And then for this second one here, it's still the positive part of the x plus 4. However, this time it's a negative part of the 2x plus 3. I'm just going to give you the answers to that. For this one, you get x equals 1. For this one, you get x equals minus 7/3. It's not an inequality. We're just solving, so that's it. That's the answer. So the last one was an inequality question, right? Where we had to put it in inequality. This is just solving. Okay, let's move on. We've got an exponential one here. So it's defined by the domain x belongs to real numbers, but x cannot equal ln2. Find f to the minus 1 of x. So we'll do this one actually. Just a bit wary of time. So y equals e to the x over 2 minus e to the x. Now, what you're doing is you're making x the subject, essentially. So I'm going to bring the 2 minus ex up. So y equals 2 minus ex equals e to the x. Let's expand the bracket. So we get 2y minus y e to the x equals e to the x. bring everything that's got e to the x over to one side. So I'll plus yex to the other side, and I'll deal with that y after. So 2y equals e to the x plus y e to the x, because I just want all the x's on one side. Now I can factorize out that e to the x because it's in both terms. So 2y equals e to the x 1 plus times 1 plus y. Yeah. Okay, so divide by 1 plus y over to the other side because I don't want that. I just want x by itself. Do over here. So 2y over 1 plus y equals e to the x. Now, how do I get x by itself? So what I use here is a little log trick. So 2 cubed equals 8. So log 2a equals 3. Just so I remember the order of what to do it in. Even though we are going to get ln here, so the natural log. Remember that ln is log e. They're the same thing. Not like that. Okay, so we get log e 2y 1 plus y equals x, which that log e is the same as ln. So we've got x as a subject now, x is by itself. So therefore, we found f to the minus 1 of x. Make sure you change all them y's back to x's. We get ln 2x over 1 plus x. Okay, so that's my inverse that we just found. It says, write down the range of f minus 1 of x. Well, we've got the domain, so that's just essentially turns into the range. So f to the minus 1 of x belongs to real numbers. And f to the minus 1 of x is not equal to ln2. So it's just that understanding thing again. Okay, question 7. I'm going to quickly whiz through this one, just wary of time. We've still got quite a bit to cover. So this diagram here, so part A, we've got f of x. We've got a and b on separate diagrams. Sketch 2f of x minus 1. So that's going to stretch it to that way. So double by everything, and then it's going to shift it down by minus 1 in the y. So let's sketch that. So if it's elongating by 2, let's say the shape becomes like that. Okay. And then this point over here, we're doing 3, so it's the y, sorry, that's changing by 2. So the 3 stays the same, it's still at 3. Minus 4 times 2 is minus 8, but then it's going down minus 1 as well. So minus 8 minus 1 is minus 9. And this point over here, 7 stays the same. It's still the same on the x, it's the y that's changing. 5 times 2 is 10, because it's stretched up to 10, and then it's minus 1, so 10 minus 1 is 9. The modulus of x with this one, so part B, everything that's in the negative part. So you can see the negative part is here and here. We're just reflecting that upwards. So the graph that we end up getting is, so looks like that. This curve is going to come up. That's already up. And then this is going to just shoot up as well. So that's the modulus, where these points just stay. That changes to 3, 4. So the x stays the same. The minus 4 has become plus 4. And this has stayed the same. That's just 7, 5. Okay, so that's modulus with curves. Okay, let's move over to coordinate geometry. So there's straight line equations, which usually use the form y minus y1 equals x minus, m times x minus x1. Still be aware they could use your y equals mx plus c over here as well. So just be aware of both of them. Don't just learn just this in one version. Gradient and intercept. So gradients change in y divided by change in x. Parallel and perpendicular lines. So parallel lines. Can't write down everything. I'm going to send you all these out after, so you don't need to write anything down. The issue is there's so much content to cover. So I want to cover as much examples as possible. And then you got it to yourself as well. So what I would say is try and understand everything that I'm going through. But if you do want me to slow down, I'm just not going to end up going through everything. So parallel just basically means same gradient. And perpendicular means it's going to have the negative reciprocal gradient. So perpendicular, that's going to be the negative reciprocal. I know these are all GCSE content that you do need to know, but the thing is, they get applied like in a more harder concept, maybe in terms of exponentials, in terms of logs, in terms of trig, and so on. Distance and midpoint, circle equations, and form x squared plus y squared equals r squared is a GCSE form, but the center can change. We've got tangents to circles and then discriminant. So remember with the discriminant, that's the b squared minus 4ac. If it's less than 0, there's no real roots. If it's equal to 0, there's one real root. And if it's more than 0, there's two real roots. So just know that that comes from the quadratic formula. If it was less than 0, it makes sense for there to be no real roots, because in the quadratic formula, this has a square root. So if it was negative, you can't square root a negative number. So that's how you can remember it. Now let's have a look at some of these questions. But yeah, don't try and write everything down. I'm going to send you all these out anyway after. The equation x squared plus kx plus 2 equals 0, where k is a constant and it has no real roots. So as soon as you see no real roots, you should be thinking, okay, b squared minus 4ac is less than 0. Find a set of possible values of k. So where we know a is 1, b is k, and c is 2, plugging them in, so we get k squared minus 4 times 1 times 2, so 4ac. We're showing that's less than 0. K squared minus 8 is less than 0. Solving that, we get k squared is less than 8. So k is more than plus or minus 8. So to write that as a set, you could say k is between, it has to be less than root 8, or it has to be more than the minus root 8. Okay, moving on. So yeah, if it said has one root, then it would like equal to 0. If it has two real roots, you'd make it more than 0 and then solve it as well. Okay, points A and B have these coordinates where k is a constant. Given that the gradient of AB is a third, show that k is 4. So we know gradient is change in y divided by change in x. Just give me 2 seconds. Okay, so as I was saying, gradient is change in y divided by change in x. So we're just doing that, we're solving for k. So for part A, change in y, which is 8 minus k plus 2, over change in x, which is 2k minus 3 minus 1. And that equals a third. And this is essentially what we're solving to find out what k is. I'll give you the answer to k. You can work this out in your own time. So k equals 4. Okay, part B, find the equation of the line that passes through A and B. Well, we now know what the value of k is, so substitute that value of k into one of them. I'll choose this first one here, so we get minus 1, k which is 4, 4 plus 2, which is 6. And then we know what the gradient is. The gradient is just a third. So you just plug in everything into y minus y1 equals x minus x1. We've got a coordinate, we've got a gradient, so you should just be able to work it out. So we get y equals a third x plus 19 over 3. Sometimes they'll tell you what form to give it in. If not, just give it in the form y equals mx plus c. Part C says, find the equation of the perpendicular bisector of A and B. Give your answer in this form. So yeah, in this equation, they told you the form. Now, perpendicular bisector means right through the middle of A and B. So let's say that's A and B. Perpendicular bisector would be right in the middle of it, and it meets at a right angle because it's perpendicular. So with it being perpendicular, the gradient is going to be the negative reciprocal of that, right? So the perpendicular gradient is just going to be, change the sign, so it goes from positive to negative. You flip it over, you get 3 over 1, and 3 over 1 is just 3. So we know our gradient is minus 3. Now bisector is the middle of both A and B. So what I need to do is, I need to find what's the middle of the A and B. So I know A, the coordinates of A is minus 1, 6, which we worked out here. The coordinates of B, I just need to substitute 4 into here. So 2 times 4, which is 8. Oh no, there's a minus 3 there, sorry. So 5, 5, 8. And then to work out the midpoint of both of them is you add them together and you divide by 2. So the midpoint is minus 1 add 5 divided by 2, which gives you 2. 6 add 8 divided by 2 gives you 7. So we've got the midpoint. So there you go. We've got everything we need to find another equation. So we've got the gradient and we've got a point. Substitute that into y minus y1 equals mx minus x1, and rearrange the formula. You end up getting 3x plus y minus 13 equals 0, because I've put it in that form there. Okay, moving on. Line L has equation, that line L2 has this equation where m is a constant. It says L1 and L2 are perpendicular. So if they're perpendicular, the gradient's going to be the negative reciprocal. So all I need to do is find the gradient from this one here. So gradient of L1, and all you do is you need to make it in the form y equals mx plus c and find out what m is. So rearranging that to give you y equals mx plus c, you get y equals minus 2x minus 7 over 2. So the gradient is just minus 2 of L1. So therefore, the gradient of L2, if it's perpendicular, is going to be the negative reciprocal. So minus 2 changes to positive. Remember, minus 2 is minus 2 over 1. Flip that 2 over 1 over, you get a half. The gradient is a half. So find the value of m. M is just a half. That's what they've said. Part B, find the coordinates of the point where L1 and L2 meet. All we're doing is we're just solving the equations. So we've already changed this. Is that minus 2x? Okay. So y equals minus 2x minus 7 over 2. That's the equation for L1. For L2, all I have to do is substitute m into here. So y equals m, which is a half x plus 4. So y equals a half x plus 4. Now, because they're both y equals, we're just solving them simultaneously by making them equal to each other. So minus 2x minus 7 over 2 equals a half x plus 4. And you're just solving that. Bring the x's all to one side, bring the numbers all to one side. You end up getting x equals minus 3. But we're not finished there yet. It says find the coordinates of the point where they meet. So I found the x, now I need to find the y. You just need to substitute it into any of the above equations. You'll get the right answer because they both meet there. When you substitute it into one of these two equations, you get y equals 5 over 2. Make sure you write it as coordinates, so just leave your answer like that. So your coordinates is minus 3, 5 over 2. Okay, now we've got circles. Now, circles are of the form x minus a squared plus y minus b squared equals r squared, where the center is AB. So you take the opposite signs from the inside, and your radius is just r, so you square root it at the end. So over here it says, circle has this equation, find the coordinates of the center of C. We just have to complete the square in order to find the coordinates of C and the radius. We have to get it into this form. So what you do is you get all your x's together and you get all your y's together. So we've got x squared minus 2x plus y squared plus 6y equals 26. And we're completing the square of each of them. So for this one over here, we've got x minus 1 squared. The minus 1 squared is 1, which we don't want, so we minus that 1. Plus y plus 3 squared, because we half that 6. And then 3 squared is 9. We don't want 9, so we minus 9. And that equals 26. Gather all your numbers over to the right-hand side. So we get x minus 1 squared plus y plus 3 squared. Minus 1 minus 9 is minus 10. Bring the 10 over to the side, you get 36. So now we can work out the center and the radius. The center is the opposite signs of the inside. So for the x, we've got 1, and for the y, we've got minus 3. And then the radius is just the square root of 36, which is just 6. Okay, so that's the equation of a circle form you need to be aware of. Let's have a look at this one. Circle has this center and passes through this point. Find an equation for C. So we already know it's going to be of this form over here. So what we can do is x, not minus 2, but plus 2 squared, plus y minus 3 squared. And we don't know what the radius is. They've not told us the radius. So in order to find the radius, because we've got 3 unknowns, we've got x, y, and r unknown. We only want 1 unknown. So what I can do is I can substitute a value of x and y, which is this one, into the equation to find out what r is. So I can substitute, sorry, not the center. It doesn't pass through the center. You substitute this point that it passes through here. That's what I told you. The center is just the center of the circle. That's not where it's passing through. So you substitute 1, 8 into this equation. So we get 1 plus 2 squared, y 8 minus 3 squared. That equals r squared. So for r, squared, we end up getting 34. So all we do is our final answer, x plus 2 squared plus y minus 3 squared equals 34. That's our answer. Part B says show that the point 3, 6 lies on the line. Well, all you need to do is you just substitute 3, 6 onto the left-hand side, and it should equal 34 when you plug that in. So you do 3 plus 2 squared plus y, not y, sorry, 6 minus 3 squared. When you put that in your calculator, you end up getting 34, and 34 equals 34, right? So you just prove that it's on the line. Okay, part C. This does tend to come up on GCSE now. They've pulled this down. So part C, find the equation of the tangent to C at 3, 6. Give your answer in this form. So it's a straight line. Now I'm just going to do a little sketch. This is going to be, let's actually make it kind of accurate. So this center is minus 2, 3. So minus 2, 3 is roughly here. It has, let's say it looks like that. That's what the circle looks like. And the tangent at 3, 6 is going to be roughly here. So the tangent, imagine it's touching the circle. That's a terrible sketch. Yeah, that's the equation we need to find of that line there. Now, the issue with this is we don't know what the gradient of that line is, and we can't work out the gradient because we've only been given one point. We only know the point that it touches is 3, 6. We don't know any other point there, and we don't know where it crosses the y-axis. So what we have to do is we have to use a different line, and that's the radius. So I'll draw that in red. We can work out the gradient of this radius line because we know that the center of this circle is minus 2, 3, right? That's minus 2, 3. So I can work out the gradient of the radius. And why that's going to help me with the tangent is because the tangent and radius, one of your circle theorems is that it meets at 90 degrees. So once I find the gradient of the radius, I just use a negative reciprocal, and that's the gradient of the blue line, the tangent. So the gradient of the radius is just a change in y divided by the change in x. So 6 minus 3 over 3 minus minus 2 gives you 3 over 5. So therefore, the gradient of tangent is just a negative reciprocal. So you change it to minus, from positive to minus, and you flip it over 5 over 3. Okay, so we've got the gradient. We're just substituting into y minus y1 equals mx minus x1. We've already got a coordinate on this line. We've got the 3, 6. We just plug that in. We plug our gradient in, simplify it, and we end up getting 5x plus 3y minus 33 equals 0. Okay, so that's that one there. So sketches do tend to help as well. If they don't give you a sketch, do put that down. Okay, section 4, sequences and series, really vary that we've only got 50 minutes-ish. So, okay, you need to know about arithmetic sequences, so they can be adding or subtracting as they're going along. Geometric sequences, that's timesing as you're going along. We've got some formulas, and the sigma notation, and some to infinity, so geometric only. So this is what you're given in the formula booklet. You have to memorize what's the form of the arithmetic series and the form of a geometric series. So I've got a question from each, so you've got an example of each. But what you get given in the formula booklet is just a sum of the n terms. So for example, sum of 20 terms, for example, for an arithmetic series, where a is the first term, and then we've got the common difference, so d. And then for the geometric series, we've got, again, sum of n terms, and we've also got sum to infinity as well. So let's have a look at this first question. It says the fifth term of an arithmetic sequence is 5, and the eighth term of a sequence is minus 16. So the fifth term, so u5 is 5, and the eighth term, so u8 is minus 16. Find the first term of the sequence, so essentially find a. So you know for an arithmetic sequence that is un equals the first term plus n minus 1 times the common difference. You have to memorize that. You are not given this. So let me just box that. That's of an arithmetic sequence. They told you arithmetic sequence here. Let's put a little arrow there. Okay, give me 2 seconds. Okay, so that's the form that we've got. Now, to find the first term of the sequence, if we put 5 into this, so u5 equals 5, I'm using this first one, equals a, which we don't know, that's what we're trying to find, plus n minus 1, 5 minus 1, which is 4d. Then we could do the same for the next one. So u8, I'm going to put a line there. So u8 equals minus 16 equals a, plus n minus 1, which is 7, and d. So we need to just solve these simultaneously because we've got two unknowns, we've got a and d. And when you solve them simultaneously, you'll get a equals 33 and d equals minus 7. So you should be quite capable of doing that. Okay, we've got another arithmetic sequence, the series here. So we've got k plus 3, 2k plus 4, and 4k minus 2. So u1, u2, u3. Find the value of the constant k. So we know with an arithmetic sequence, they're going up in the same amount. So when you're finding a common difference, that always is the same number. So for example, plus 2. It's always going to be the same number. So using that fact, we know that if I do 2k plus 4, the second term, minus the first term, k plus 3, the difference between them two should be the same as the difference between 4k minus 2 minus 2k plus 4, because the differences should be the same. That's all in terms of k, that equation. So you just need to solve that. When you solve that, you end up getting k equals 7. Just because of time, I'm just going to skip through, but you can do this in your own time as well, work through it. Find the sum of the first 20 terms of the series. This is where we use our formula booklet. We're using this one here. So the sum of the first 20 terms of the series. Okay, so we need to know what A and D is in order to use this here. So the first term, if I substitute k into this, 7 plus 3, so I'm finding that. So A is 7 plus 3 because that's the first term, which is 10. My common difference is, so we could just find what's the second one here. So if that's 10, this one over here, 2 times 7, 14, 14 add 4 is 8. So the common difference is 8 because the difference between them two is 8. So the common difference is 8. Now I've got my A and D, I can just substitute into the sum to the 20 equation. This one over here, because I don't have the last term. This is if you've got the last term. And then we can just solve it. So the sum of 20 equals 20 over 2 times the first term plus 19 times the common difference. And putting that in a calculator, you end up getting 1,720. So yeah, be aware which version of the sum you're using. If you're given the last term, you use that first version. If you're given just the first term and the common difference, which we just worked out, you use the second version, which is more common one that you tend to use. Okay, we've got a geometric series now. Now remember, a geometric series is something where you're timesing up by a common ratio each time. So 3a, the fifth term of a geometric series is 12. The eighth term, so let me write this down. The fifth term is 12. The eighth term is 96. Find the common ratio. Now this time, remember how I said with the arithmetic sequence, you have to memorize this version of it. With the geometric one, this is what it looks like. So a geometric series, the form is, your term is a, which is your first term, times a common ratio to the power of n minus 1. So you need to memorize this, you're not given this. Okay, so find the common ratio. We're going to substitute both of these into here and solve them simultaneously, just like the first question that we did. Again, you have to memorize that formula. So using the 5 one, so u5 is 12 equals a, we don't know what a is, times r, which we don't know, n minus 1, 5 minus 1, which is 4. And then for the 8 one, we know that's 96 equals a, which we don't know, r to the power of n minus 1, 8 minus 1 is 7. And we're just solving these two simultaneously. And when you solve them simultaneously, you end up getting r equals 2. It says find the first term of the series. Again, using your simultaneous equations for these two, you find a, and a ends up being 3/4. So you substitute your r in and you just solve, essentially. So simultaneous equations comes up quite a lot, as you can see. Okay, part C, the sum of the first 20 terms, giving you answer to the nearest whole number. So going back to the formula sheet, we're using this equation here. So the sum of 20, we're just plugging in our A and R that we know, and that's it. You're just using the formula from the formula booklet. Make sure you know where everything is in the formula booklet as well. You don't want to be faffing around on the exam day as well. Get used to knowing where everything is now whilst you're practicing. We're using sum of 20 terms is our A times 1 minus 2 to the power of 20. Where does the 2 come from? The 2 is R, which we've just found, over 1 minus 2. And the answer we end up getting is 786,431.25. That's the answer. Okay, we've got another geometric series one here. The second term, so U2, is 3.75, and the sum to infinity this time they've told us is 20. Now the sum to infinity for a geometric series you've got in the formula booklet, as you've said here, where it's A over 1 minus R. You don't have to memorize that. Find the two possible values of R, knowing this. So we're using, so we've got 3.75 equals, so that's the second term, AR, using what we know here, right? So the second term, UN, U2, is 3.75 equals AR n minus 1. 2 minus 1 is just 1. There's a 1 there, which we don't need to write. Okay, so we know that with this first one over here, that's the formula that you need to remember. The sum to infinity one equals 20 equals A, which we don't know, over 1 minus R. Find the two possible values of R. So we're just solving this simultaneously. Whenever you're doing something simultaneously and they say work out the two possible values, most likely this is going to turn into a quadratic, which it will. What I can do is I can times this 20 up by 1 minus R equals A. I end up getting 20 minus 20R equals A. And I substitute this in for A over here, and you'll see a quadratic forms. 3.75 equals A, which is 20 minus 20R times R. So you can see there's that quadratic that forms 20 minus 20R times R. We're going to end up getting R squared. So what we're solving is, the equation we're solving is 20R squared minus 20R plus 3.75 equals 0. So solving that, we end up getting R equals 3/4 or R equals 1/4. Okay, part B says find the corresponding two values of A. So all you need to do is just choose one of these equations. I'll probably choose that one and substitute both of your R's inside and see what you get for A. So when I let R equal 3/4, then A is going to equal 5. If I let R equal 1/4, so what we just found, then A equals 15. So you're just plugging them in. It doesn't matter which equation you choose. Okay, then part C, I'll do over here. Find the smallest value of n for which the sum of n is more than 19. So the smallest value of n, so how do I know which R to take? Oh, it says it here. Given that R takes the larger value of the two possible values, so the larger value, R is 3/4, so you're going to let R equal 3/4. So when R equals 3/4, I know A equals 5. So yeah, they've told us that in the question which R to choose. And we're saying find the smallest value of n for which sum of n is more than 19. So the sum of n equation, which is over here, we're just making this equal to 19 and solving for n. And we've got our A and R. So the sum of 19, so 19 equals 5, our A value, 1 minus our common ratio, which is 3/4 to the power of n, which is what we're solving for, over 1 minus R, which is 1 minus 3/4. This is going to end up being a log question because we've got n in the power. Okay, so if I do 1 minus 3/4, that's 1/4. 19 times that quarter. So we end up, so once simplifying and getting that 3/4 to the n by itself, we get 3/4 n equals 1 over 20. And we're using our log rules here. So log of 3/4 1 over 20 equals n. So when you put that in your calculator, n ends up being 10.4. So we can't have n as a decimal number, right? N has to be an integer, it's a term. And it can't be 10 because we've passed the 10th term. So therefore, you're going to say n is the 11th term. That's your answer. Okay. Right, let's move on. Okay, so we've got the sigma notation here. So sometimes it's not arithmetic or geometric, they'll just give you some sigma notation. They said find u of 3 and u of 8. Now, just reading what this says, this is for this first term between k being 0 and we've got n, we've got k squared plus 1. And then for the second term, we're minusing the n minus 1. So u of 3 equals, we're substituting for the n 3, so sum between 3 and k equals 0 of k squared plus 1 minus the sum of n minus 1, so 3 minus 1, which is 2, where k equals 0 of k squared plus 1. So we're just plugging in the values and see what happens. So we end up getting when k is 0, 0 squared add 1, which is 1. Now let k equal 1 because it's a positive integer, so we're going up in 1, 2, 3, up to 3. Now the next one, plus k equals 1, 1 squared, which is 1, 1 add 1 is 2. Let k equal 2, 2 squared, which is 4, 4 add 1 is 5. And then finally 3, 3 squared, 9, 9 add 1 is 10. So that's for the first one. Now we're doing it for the second one in minusing, because there's a minus there. K being 0, 0 squared add 1 is 1. 1 squared add 1 is 2. And 2 squared add 1 is 5. So we don't do 3 here because it's up to the sum of 2. So we just get 10. And then we do the same thing with 8. So u to the 8, the sum between 8 and k equals 0 of k squared plus 1 minus the sum between, it says n minus 1 up there. So 7, k equals 0, k squared plus 1. And then you're just working it out, essentially. And then you end up getting 65. Same as before. Okay, moving on. We've got a geometric series, so we've got the first term, second term, and the third term. Find the sum to infinity. So we know a equals 12 because the sum to infinity equation, I'm not going to scroll up just because it's going to waste time. Sum to infinity is a over 1 minus r. So we've got a, which is the first term, which is 12. And then r, we just need to figure out what am I timesing by each time. So we're just doing 9.6. 9.6 divided by 12, which we end up getting 0.8. Okay, so to find r, I've just done 9.6 divided by 12, which gives 0.8. You could have even done 7.68 divided by 9.6. You just do the term after divided by the term before to work out the common ratio. So now that we've got a and r, we just plug that into the formula for sum to infinity, which is 12, the first term, divided by 1 minus r, which is 0.8. So we end up getting 60. Okay, now let's move over to trigonometry. So you need to be, let's have a look at some of these. So when solving trig, some people use CAS diagrams, some people actually use the diagrams for sine, cos, and tan. I use the diagrams, but it's up to you. Make sure you're familiar with pi radians is 180, so pi over 2 is 90. So make sure you're quite confident with your conversions. We've got tan equals sine over cos, sine squared plus cos squared theta equals 1. You have to memorize these, you will get given these. Even these bottom two here, they tend to trip up quite a lot of people. You have to memorize them as well, but if you don't memorize them, to derive these, all you have to do is this first equation, divide the equation by sine, and you'll get one version, and then divide it by cos, and you'll also get the other version as well. So yeah, if you don't want to memorize them, you can always derive them, but then it just wastes time in the exam as well, right? So what else do you need to know about here? But yeah, make sure you memorize all them ones. So solve for the equations between 0 and 180, this equation here. You can let 3 theta minus 15 equal x, and then solve it for x, and then substitute it in if that's easier for you, or you can just jump straight into it. It doesn't really matter. So 3 theta minus 15 equals, you're doing the inverse sine of 0.7 to find your first solution. And for the first solution, you end up getting 44.4 degrees. You can use the sign diagram or cast. It's up to you what you want to use to find the further solutions. But what you need to remember is this is 3 theta minus 15. So 3 theta minus 15 is going to change this interval up here. So make sure you include all them as well. So whether you're changing it to U or using a different letter, make sure you include all the values. So I'm just going to write the answers down just because of time. So 404.4 degrees, 495.6 degrees. Now each of these answers, we've not solved for theta. 3 theta minus 15 equals all these answers. So to find theta, to each of these, I need to add 15 and then divide by 3. And for each of them, you get 19.81 degrees, 50.19 degrees, 139.81 degrees, and 170.19 degrees. And as you can see as well, just making sure all my values are between 0 and 180 as well. Had I missed out these ones here, which are quite common, you would have ended up missing 2 answers as well. So just be careful of that. The interval changes if it's not just sine theta or sine x equals. Okay, the next one with tan, same thing as last time. So theta plus 30 is the inverse tan of minus 2.5. And with this, what's quite good about tan is, if you have a look at the graph, you can just add and subtract 180 because that's the interval that is occurring in every 180. So to work out your solutions. So I end up getting minus 68.2 degrees, putting it in the calculator, for theta plus 30. If I add 180 to that, I get 111.8 degrees. It said to give it to 1 decimal place. And to finally work out what theta is, I need to minus 30, and then you find out what 30 is. So minusing 30 from each, we get minus 98.2 degrees and 81.8 degrees. Are they in the interval? Yes, they are. Okay. Wanted to just show you this example just on how to tackle a square. So we've got tan squared x equals root 3. We've got 2 different versions to work out. So tan x equals root 3, right? But you get 2 answers, you get plus and minus. So we need to do tan x equals minus root 3, and we need to do tan x equals plus root 3. So we've got 2 different things that we're working with, so be careful of that. You'll end up missing solutions. So what do we get? When we let it equal the positive version, we get x equals 60 and 240. So to 60, just add 180. And for this version here, you end up getting minus 60, 120, and 300. Again, just add 180. So these are all your solutions. Are they all in the range? No, minus 60 isn't. We eliminate that one because minus 60 isn't in the range. So in the range, we've just got 120, 300, 60, and 240. They're your 4 answers. Okay, now we've got a bit of using the equations and proofs. I would highly probably recommend when you're doing the real exam, just leave this last because sometimes they give you the follow answer anyway to work it out. So for example, here they said show that this looks like this and hence solve the next one. So even if you didn't know how to show this, you could still do part B because you can use what's in the first one to work it out. So for 4A, let's do part A. So show that this can be written in this. Now we're just looking for patterns. I can see that from the first equation to the second, there's no sign at all. So therefore, we're going to be changing the cos that's in the first equation. No, sorry, the sign that's in the first equation to cos because I don't want any sign. So I'm going to and always say which identities you're using. So I'm using cos squared x plus sine squared x equals 1. Rearrange that. You end up getting sine squared x equals 1 minus cos squared x, and we're substituting that in for here. We get 2, 1 minus cos squared x equals 7 cos x plus 5. Expanding that, we end up getting this. And bringing everything over to the right-hand side, we get 2 cos squared x plus 7 cos x, and then 5 minus 2, which is 3. Yeah, that was quite straightforward on that one, but yeah, they do get more complicated. And then for part B, hence solve. Now you should recognize that is a quadratic equation. You're going to end up getting the 2 answer thing again. If you're not comfortable with working with that cos x, just let cos x equal I don't know, y, for example. And then you could change the equation to 2y squared plus 7y plus 3 equals 0. So it just looks a little bit less daunting when you're solving it, or you can just leave it as cos x as well. It's up to you. When factorizing that, or you can use a quadratic formula, you end up getting 2y plus 1, y plus 3 equals 0. So therefore, y equals minus a half, or y equals minus 3. And we've just said y equals cos x. So that basically means cos x equals minus a half, or cos x equals minus 3. Now, if you think about the cos graph, cos is just between 1 and minus 1. So it's not possible for this to be true. Cos x being equal to minus 3, that's impossible. So we just totally disregard that. And just like before, just work out what x is for this one here. Between the interval 0 and 360, we end up getting 120 degrees and 240 degrees. That's the answer. Okay, this was an interesting one. So this was surds being mixed in with trigonometry and identities, essentially. So it says, given that cos 75 is that and sine 75 is that, show that tan squared 75 can be written in this form. Now, you should realize that tan is sine over cos, right? Tan, I'll just say theta equals sine theta over cos theta. So to work out tan 75, I could just do sine 75 divided by cos 75. So I could just do root 6 plus, that does not look like a 6, that looks like a b, root 6 plus root 2 over 4 divided by root 6 minus root 2 over 4. We're dividing two fractions, so we're doing keep, change, flip, right? So keep, change, flip. When I flip that second fraction, the 4 is going to end up on the top, and we can cancel both 4s out. If the 4's up here, we can cancel it out. So the 4's disappear, and we just end up with, if you can't visualize that, just write it down and you're working out. But we end up with root 6 plus 2 over root 6 minus 2. And what you have to do is, even though it doesn't say rationalize, you should always just rationalize the denominator if there's a surd there. And when you rationalize it, you get 2 plus root 3. But we're not done. That's tan 75 that we just found. We need tan squared. Okay, so we need tan squared 75. So what we've just found, we need to square. So 2 plus root 3 squared is just 2 plus root 3 times 2 plus root 3. Expanding that, collecting like terms, you end up getting this. So yeah, I found that quite interesting that they mix surds and trig identities together. Okay, so here's some other graphs that you need to know. There's a really common misconception as well. Sine to the minus 1 of x is not equal to 1 over sine x. That's a really common misconception. 1 over sine x is cosec x. Let me just write theta just to keep it in line with what's there. 1 over tan theta is cot theta. And then 1 over cos theta is sec. Okay. So yeah, you are used to like, okay, if something's to the minus 1, it's a reciprocal. That's not true for trig. So if you're asked for the sine to the minus 1 of x graph, that's not 1 over sine, and don't end up drawing this one here. It's this one here, and that the domain and the range you need to remember as well. So you need to remember all these. With the second cosec one, you should just notice, so with the sine graph looks like this, right? So it's the same thing, but it's gone upwards, basically. So yeah, with the cosec, if cosec theta equaled, I don't know, 0.5, that's not possible because you can see the graph doesn't exist for there. So when you're solving these equations, keep the graph in mind as well as to where they are. Okay, just really wary of time. We're definitely probably not going to get through all of this, but we've covered quite a lot. Question 6. Okay, so solve for theta being between 2 pi and 0. So we're using gradients here. solve this equation here. So let's bring the 2 over to the other side. So we get cosec theta equals 5 over 2. Cosec is 1 over sine theta equals 5 over 2. So to bring sine theta up and then bring 5 over 2 down, ends up flipping the fraction. So sine theta equals 2 over 5. If you can't visualize that, just do keep change flip and then just work it out longwards. And then using the usual methods that we've used, you'll find your solutions in radians. And then what I find that helps as well, that change that 2 pi to like a real number, so you can visualize that, okay, is this number between, so 2 times pi, like around 6 point something. So you can just visualize where your numbers need to be between as well. Okay, this one here, solve this equation, given your answer in terms of pi, so we're just leaving this accurately, we're not putting it in the calculator, but the issue is we've got cot and we've got sec. We need just one trig function. Now you should know cot x is 1 over tan x, and we know tan x is sine x over cos x. So combining these two together, cot x equals 1 divided by tan x, and tan x is sine x over cos x. So keep change flip 1 times cos over sine. So we could say cot x equals cos x over sine x. Again, you can derive it just like I have, or you can just remember that it's the other way around, but that's the reason why. So I know cot x is cos over sine, and I know sec is 1 over cos. So let's put that in. So 2 cos x over sine x equals 3 over cos x, because sec x is 1 over cos. Okay, so I still don't want cos and sine, so let's times up the denominators because we don't want fractions as well. So timesing up the sine over there and cos over here, we get 2 cos squared x equals 3 sine x. That cos squared x, we know the identity sine squared x plus cos squared x equals 1, so I can change that. So to 2, 1 minus sine squared x equals 3 sine x. So I've got everything in terms of sine now, so that works perfectly. So expanding that, I get 2 minus 2 sine squared theta equals 3 sine x. You should recognize you've got a quadratic here. We're going to end up getting 2 answers down. Bringing everything over to the right-hand side, I get 2 sine squared theta plus 3 sine x plus 2 equals 0. And you're just solving this quadratically, so we end up getting, I've randomly changed to theta for some reason. Let me just change them to x's. Don't know why I've changed to theta. Okay, so sine x could equal, when solving this, a half. You could use quadratic formula, you could use calculator or whatever to solve this. Well, sine x equals minus 2. Sine is between 1 and minus 1. This is not possible. Minus 2 is not on there. If you put that in calculator, you'll end up getting an error anyway. So working this out in terms of pi, getting your first answer from the calculator, you get a 6 pi. You can use your graph or you could use cast diagram to work out the next, but that's 5/6 over pi. And there are your answers for that one. Okay, so this is what you get given in the formula booklet. So we've got, you do not get, these are not in, hold on. These are not in formula booklet, but the rest is. So we've, okay, so we've got these here, which we use to derive the double angle identities. So it's up to you. You can either memorize them or you can derive them from the formula booklet. And we've also got the small angle approximations as well, which is also in the formula booklet as well. So let's see what the next question is. Okay, we've got a small angle approximation question, so I'll show you how to do this. Given that theta is small, use a small angle approximation for cos theta. So if I just show you what it is for cos theta up here, cos theta is, let's put this down here. Cos theta is estimated around 1 over theta squared divided by 2. Okay, so that's the approximation we're using. They'll tell you which approximation to use to show that this is estimated to be that. So for part A. So, okay, so for cos theta, which is 4 times cos theta, which the small angle approximation is 1 minus theta squared over 2. Then we've got plus cos squared 2 theta. Be careful of this 2 theta. That's going to end up being 1 minus, not theta squared, but 2 theta all squared over 2, and then that's all squared. Okay, so we need to expand and simplify and stuff with this. So for this one here, we get 4 minus 4 over 2, which is 2, so we just end up getting 2 theta squared, plus in here, we end up getting 1 minus 2 theta squared is 4 theta squared, and then 4 divided by 2 is just 2 theta squared, and then that's all squared. And then when you expand and collect like terms, you end up getting 5. I should not even be using the equals. I should be using. We get 5 minus 6 theta squared plus 4 theta to the power of 4. So you'd have to expand and collect like terms. To the power of 4 ends up coming from here. 2 theta squared times 2 theta squared ends up giving 2 theta 4. Is that what it is? Yeah, it is. Okay. Part B says, hence find an approximation of this when theta equals 3. So even if you couldn't do the first question, you could still do the second one. All we're doing is we're letting theta equal 3 over here. So 5. Oh, actually, hold on. They've told us when theta equals 3 degrees, but we have to change that to radians. So 3 degrees is, yeah, we have to change that to radians. 1 over 60 pi radians. So to work that out, all I do is you do 3 times pi over 180. You times it by pi over 180 to change your degrees to radians. Yeah, that's what you do. Yeah, that's what you do. Okay. And then it's the other way around if you're going the other way around. And then you're substituting 1 over 60 pi into here. So we end up getting 5 minus 6 times 1 over 60 pi squared plus 4 times 1 over 60 pi to the power of 4. You end up getting 4.98358. That's the answer. Okay, part C says, calculate the percentage error in your approximation. This is quite a common final question with these small angle approximations. We just want to see how accurate is our answer. So what you have to do is you have to actually work out, okay, what is the value of this using your calculator. So in your calculator, substitute 4 times cos 1 over 60 pi plus cos squared 2 times this, so 2 over 60 pi. And what answer do you get? You end up getting 4.98359. So you can see it's literally just that last digit. Now to work out the percentage error, you just do the new one, so 4.98359 minus the original 4.98358 divided by the the one that it's changed by. So 4.98359, and you just times it by 100 because it's percentage, so you end up getting 0.000225% expected. It's just literally the 5th decimal place that's changed, so it is quite accurate. Okay, so I've put this here just so I could show you the formula for each of the arc length and the sector area. So arc length, when we're using radians with this, by the way, not degrees. This is radians because we've got the 1.2 there. It's told you 1.2 radians. The arc length is r theta, length of the arc. The area of the sector is 1/2 times r squared times theta. You need to memorize both of them. You're not given them either. So for part A, the length of the arc is r theta. So r times theta, r 9 times the 1.2, we end up getting 10.8 centimeters. And then for part B, calculate the area, we've got 1/2 times r squared times theta, we end up getting 48.6. So yeah, you need to memorize that version. And that version only works with radians. Okay, quite wary of time. So what this essentially is this is using the double angle identities that's above. So they've told you by writing sine theta as this, show that it equals to this. Using the double angle identity above, which is in the formula booklet, sine A plus B is sine A cos B plus cos A sine B. That's in the formula booklet, just to show you. This one over here, I've just taken the plus version, where you're letting A equal 2 theta and you're letting B equal theta, so you're just sticking them in. So sine A, which is 2 theta, plus theta is sine 2 theta cos theta plus cos 2 theta sine theta. Now, therefore, so sine 3 theta, which is what we're working, we need to show that it looks like this. So just everything, just in terms of sine. So I need to get rid of all the causes somehow. Sine 2 theta, that's a double angle identity, which you should know is 2 sine, let me just highlight so you know that's the double angle identity there, which is 2 sine theta cos theta. And the reason why I want to change that, and I know I need to change that, you can see my final answer has no 2 thetas in it, it's just got theta in. So that's why it's quite obvious to get rid of the double angle. So we've got 2 sine theta cos theta, which is sine 2 theta, times cos theta, plus we've got a double angle identity here. So for cos 2 theta, in terms of sine, remember there's a few different versions. The sine version is 1 minus 2 sine squared theta. Personally, I probably would derive the double angle identities because it sometimes it's quite tricky just to make sure. So sine theta. So we changed these double angle ones because we can see in the final answer there's no double angle identities. So let's calculate terms. So 2 sine theta cos theta times cos theta is cos squared theta, plus 1 times sine theta, which is sine theta, minus 2 sine squared theta times sine theta is sine minus 2 sine cubed theta. So I can see where that cube's coming from. Okay. We need to get rid of that cos because there's no cos in my final answer, and cos squared theta is the same as 1 minus sine squared theta. So 2 sine theta, 1 minus sine squared theta, then plus the sine theta, minus 2 sine cubed theta. Expand that, 2 sine theta minus 2 sine or cubed theta plus sine theta minus 2 sine cubed theta, and collect like terms, we end up getting 2 sine theta plus sine theta is 3 sine theta, which is here, and then minus 2 sine cubed theta minus 2 sine cubed theta is minus 4 sine cubed theta. So I just wanted to show you the thought processes that go when you're actually proving that something can be written as a certain thing. That's the reason why they give you the answer in the question. They want you to work towards that and notice that, okay, it's just in terms of sine. We've got just one single angle, therefore use double angle identities to get rid of it as well. It's even prompted you as well to use the addition formulas. It's prompted you to push it into that as well, which is quite nice. Okay. Right, just wary of time, so I'm just going to speak through the next few and not actually work through them. Okay, so prove this identity. So similar to what we were saying before, I can see the final one's just in terms of cos and sine. So there's a double angle identity here. I need to use a double angle identity to get rid of the 2x just to x. And that's what you do there. Okay, so these ones here where you have to put it in the form r cos x plus alpha. To find r, you use Pythagoras' theorem, and to find alpha, you change sine over cos to tan to work it out. Just wary of time. So again, for question 13, prove that this identity is equal to tan 2x. So what I would do in this case is tan 2x, I would work out what is the double angle identity for that. So tan 2x is 2 tan x over 1 minus tan squared x. So this over here, I need to somehow get it to look like that over there. So the sine, change it to tan, the cos and the sec somehow needs to become 1 minus tan squared x. And I can realize I can divide the top and bottom by cos, and it helps getting that, because sine over cos is tan, cos over cos is just 1, and sec over cos, you'll end up getting the same thing when you do keep change flip as well. Okay, so yeah, that's the mindset with that. Okay, exponentials and logs. I'm going to skip past this one. This is AS content, to be fair, but you do need to know it for A-levels as well. Okay, differentiation, I'll speak a little bit about this. First, principles definition. You're given that in the formula booklet, so I'll show you what it is. Where is it? Yep, so it's here in the formula booklet. You get given that. I think I'm going to have to do another session probably to go over the last half of this booklet. So f of x equals that. We're finding f of x and we're finding f of x plus h, and you just plug everything into the formula. Okay, what else have we got? Power rule, we've got product rule and quotient rule. So the product rule, you are not given this, you have to memorize this. So dy over dx equals, if you've got y equals u times v, then dy over dx is u times the differential of v plus v times the differential of u. You have to memorize that. The quotient rule is given in the formula booklet, but not in the form that you like it. It's given like this. So I'd probably say it's better off memorizing it rather than using this. So essentially, if I've got y equals u divided by v, so quotient means divide, then dy over dx equals u times dv over dx minus sorry, wrong way around, v times du over dx. V times du over dx minus u times dv over dx over v squared. So it's up to you if you want to memorize it, but it is in the formula booklet, but in terms of f of x and g of x. Okay, so that's quotient rule when you're dividing. Chain rule is when you've got a function inside a function. You have to differentiate both, essentially. And chain rule just basically says dy over dx equals dy over dt times dt over dx. And the reason why that works is because these cancel out with each other. So that's why it works. Some of you might be using du for that. I wouldn't recommend using du. You get confused with the product rule then if you're using u's there. Implicit differentiation is where we've got a mixture of both y's and x's. So you implicitly differentiate. All the normal differentiation you do is called explicit differentiation. Parametric is when you've got two parametric equations. It's using chain rule, kind of. You've got two equations given in terms of another function, so in terms of another variable, sorry, in terms of t. And you solve that way. Tangents, normal, stationary points, and so on. You need to know the definition of differentiating. So differentiating is to find the gradient function. Okay, if I make it equal to 0, that's the stationary points. If I then differentiate again, the second differential will tell me the maximum and minimum points, and so on. And then essentially differentiation is rate of change. So yeah, there's some questions here, unfortunately, we won't be able to go over. This is also given in the formula booklet as well, so you don't need to remember it. The differential of tan is sec squared x. It might tell you to prove it using the quotient rule. So you would say tan x equals sine over cos, and then use quotient rule and prove that. And then these are some other ones that you are given as well that you could also use for integration as well and work backwards. If they tell you to integrate something like that, you know it's just going backwards to tan. So yeah, you use that as well for that. Okay, we're going to have to definitely do this in another session. The differential of sine is cos, the differential of cos is minus sine. You have to memorize them, you're not given them ones. Whenever you're differentiating any or integrating anything to do with trig, you're always working in radians, never in degrees. We've got parametric, we've got implicit. Okay, and then in terms of integration, it's working backwards. What is integration? Well, if you've got a curve and you're integrating it, you're finding the area under that curve. If you are given the differential of something and you want to find the curve again, you integrate, but there's a constant of integration. If you want to actually work out what the plus c value is, you have to have limits, or you substitute a value that you know in. There's other versions of integration, so substitution and by parts, that'll help you with really complicated questions. But again, I think we're going to leave this to another session because there's still quite a bit to do. And then the final part of core is numerical methods, vectors, and differential equations, which we can do in a future session. But I'm going to wrap it there. It has been quite a long 2 hours. I will send the recording out and these notes out as well, so you can have a try at these questions. But it's quite a good booklet. It's gone through everything in order, and it's a checklist for everything that you need to know in core is on here. So you can use it as a checklist as well. So I'm going to end it there, and I'll get everything sent out to you. Okay, thanks for joining, guys.